Hello and welcome to CUDA Weekly. I'm your host, Johan Bontes, and today I want to talk about shared memory. Shared memory is a level 1 cache that you can address as a programmer. It doesn't get evicted out from under you. Whatever you put there stays there, and it's a mechanism for threads to share data. Now, these threads must be in the same processor. Now, shared memory is a big subject, but today I just want to focus on how fast it is. It's so much faster than global memory that you should basically use it whenever you can get away with it and you don't need to use that much space. So let's talk about it.
So here we have Compiler Explorer. It's this really cool piece of technology.
You can access it from cuda.godbolt.org.
And there they have a variety of compilers and environments that you can go through. You can even program in COBOL, various C dialects, all sorts of programming language, and of course CUDA. So it runs your code, compiles your code, and then it runs your code in the cloud somewhere, in this case on a NVIDIA Tesla T4, which is in some data center somewhere. You can type in whatever code you like, and then it will run that code. You can see the assembly here.
So shared memory is a level 1 cache that is dedicated for use by the programmer. It's not gonna get evicted from out of under you. Whatever you put there is gonna stay there until, well, you write something else to that particular location of memory. And it's about the fastest memory you can get. Let's run up an example. This code takes the current thread index, stores it in a shared array, and per warp, it will reverse the order of the index using an XOR 31, which every 32 threads will flip the sequence of the thread index. So the before data will be going up, increasing, and the after data should be going down, decreasing. Let's walk through it. We have a global function that gets called from our main with 128 threads in a single block. We accommodate those 128 threads in our shared array with 128 elements. And then we feed the current thread ID into each of those entries. This is the before entry that you see printed here, going nicely up until 128. Then we pass that on to flip as an int pointer. We can assert that that thing is indeed shared. And then we load the data from that shared array into B. Now we have a read. After that, we're going to do a write. So we do a sync warp here to prevent read after write errors. Because the thread that reads is different from the thread that writes here. There is no mix up between different warps because, well, I've manipulated so that the thread index stay in the same warp, but within the warp, there's a mix up of threads. So I have a synchronization point here. So I do not get write before read issues there. That's why there's a sync warp await. After that, I sync warp again before the print. It is not strictly necessary, but it will be useful in timing later. Then I print the data. Okay, let's add some timing to see how long these manipulations take. We started the time here Here we load the data, then we sync, and then we write the data. Now this seems suspiciously fast. 12 cycles for a read and a write. I think the optimizer has optimized some part out for us. When we look at the output from the assembler that the GPU runs, we can see the first clock being set up for the start. We can see the second clock, that times the end. And then in between, we have, now let's see, before we have a store to shared memory. And then we have the clock. We have the XOR that changes the thread ID. We have a store here, but notice that the optimizer optimizes away the read because it knows that this read and this read is actually duplicate. So it already has that data within its registers. It cheats a little and it only times the store. So the store and the synchronization here, it's translated into a no operation. It can do a not because, well, it's already done the read, so there's no contention there that it needs to work around. So only the store and some manipulations take 15 clock cycles. Now we can force the compiler to actually do the read. And when we do this forcing, we can see that the time is now increased to 29 cycles. And due to the volatile being there, see it does a load from shared memory, then it does the XOR manipulation, it does a NOP there, no operation, and then we have the store. So there we have it, 29 cycles to do a load, some manipulation of the data, and a store. Let's have a look what happens when we run this through main memory. When we do this and we force the load and store to both happen by using the volatile intervention, when I change the shared array into a global one, this device array lives in global memory. Now you would think they would have used the keyword global here, but they use the keyword device. That means that this array cannot be accessed from the CPU and the GPU, but device things can only be accessed from the GPU. So here we initialize our global array now and pass it to the flip function. When we do that, it will force both the read and the write to happen, and that time takes 289 cycles instead of 28, was it 28? So about a factor 10 times slower. Now the only reason that it's actually 289 is because that data gets stored in the level 2 cache. If it goes all the way out to main memory, looking at, well, at least double, but maybe 1,000 cycles. It's quite a bit slower than shared memory. So whenever you get the opportunity, always use shared memory because it's just so much more efficient. Okay, I would like to leave it here and I hope you enjoyed the program and I'll see you again next week.